everyone. We're going to cover multiple linear regression in this video, but very specifically simultaneous multiple regression. So let me just give you a little bit of background for how this works, which is not a supplement for the lecture. So go watch the lecture first, but here's just a little bit more if you've slept since then. What we're going to do is take several X variables, several predictors, and use them to understand some sort of Y or criterion variable. We're going to use all these variables at once, hence the simultaneous part, rather than doing them in steps, to see how each variable changes Y, and this is the important part here in italics on the end, while holding everything else constant. So while I hold all these other variables constant, what is the effect of this 1 on Y? So some definitions to remember from the lecture. B, or little b, is our coefficient. It's the value of the unstandardized slopes. This is our raw coefficient. So the interpretation of that is for every 1 point increase in X, you get B increases in Y. So if I tell you that every time that you study an hour, you get 2 points on your grade, that would be an example of a raw coefficient. Beta, however, is a standardized coefficient. Standardized coefficients are very useful if you are wanting to compare coefficients to each other that are not on the same scale because they're z-scored. So I could say, well, for every hour that you study, you get 0.25 standard deviations, which isn't super helpful, right? But if I wanted to compare that for every chapter that you read, and I said you got only 0.12 standard deviations, you would realize that studying is more useful. When you only have one X variable and one Y variable, B, beta, and R, correlation, are all the same. But we're really not going to do that because correlation is just a separate issue. We're going to look at multiple predictors. So that's why we're doing multiple linear regression. R squared is the amount of variance in the DV predicted by your IV. So that's our effect size. How much of the variance, the good variance, overlaps between X and Y. PR, just PR, is a partial correlation. And it's the variance from only that IV divided by the variance not accounted for. So it tells you how much variance your variance accounts for is when you only look at variance that you can explain. That is a terrible sentence. Oh, good grief. It basically tells you how much of the good stuff that you are explaining when you only look at the things that you can explain. Okay. So it's the proportion of variance in Y not explained by other predictors. And this is probably very confusing without that Venn diagram picture that's in the notes. So I tell you to use that. But really what PR tells me is it's the good variance accounted for divided by the bad variance after you remove the variance for everything else. So if you have removed all of the other overlapping variance. So it's a good to bad ratio when you sort of take out all the other cookies in the jar, to go back to my cookie examples. A PR PR squared is the effect size we're going to use instead of Cohen's d as for our coefficients. So there are two big overall questions to answer, much like ANOVA. So is my overall model significant? Meaning, do the predictors predict Y at all? So can we even guess at what Y is better than chance? And if so, which of those individual predictors are the most useful or are significant? So remember, this is kind of a two-step process, just like ANOVA, where I'm interested in if the overall model is significant, then where are my predictors significant? This particular data set is very cheesy. It's easy. So it's the number of books a person read and the attendance of the person in a course, and then does that predict their final grade? So the question is, do attendance and books both predict course grades? As usual, let's start with power and then work our way through assumptions, the test, and yes, even pictures. So let's do GPower first. So this test family is going to be an F test. we're going to do R squared linear multiple regression deviation from 0 because we are looking at the entire model at once rather than a step. In this particular effect size, we're going to use a small effect just for this particular example. So let's hit determine. Here you're going to enter squared multiple partial correlation is 0.01. Calculate, transfer to main. A is 0.05. Whoops. B is 0.8. And we have two predictors, books and attendance. So it tells me that I need 957 people, which I most certainly do not have in this data set. So with two predictors and a very small effect size, we need a lot of people to find that. If we consider this a medium effect size, so 0.09, calculate and transfer to main. I still have only two predictors. I don't know why it reverted that one, unless I typed it in wrong. Now I only need 100 people. So that difference of effect size is rather huge. All right, so here's the results section that you can use to help write up. I'm going to change this just a little bit because we cannot get cooks and leverage out of Excel. But let's go ahead and work through how to do all of this in Excel and JASP. So first thing I'm going to do is open my data set. So this is data set 1. I'm going to wait 87 years for Excel to open. And I'm just going to save this as a regular Excel file so we can work through it. Okay. First thing you're going to check for accuracy. So are there any scores that are out of range? Well, it's very tempting to highlight these first, which is what I always do. Remember, that does not do us any good. So I'm going to click Data, and then Data Analysis. Go up to Descriptive Statistics. Click OK. Highlight these three bad boys. Labels in the first row. Give me summary stats. Hit OK. See what happens here. Oh, good, that ran. So really here we're checking for min and max scores. That's the biggest thing I'm concerned with. So I can't really read negative books. So I'm doing pretty good. There's no negative scores. I can't negative go to class. So that looks pretty good. And then if we had an upper maximum on the number of times that you could go, that would be important. Or if there were only 3 books in the class, 4 would be wrong. But these 2 are okay. And I also cannot make a negative grade. And I really can't get over 100. So accuracy-wise, this thing looks pretty good. So let's check that one off. The second thing I want to look for is missing data. So remember, I'm going to change this to my master data set and not screw with it. So let's look for now missing data. You, come over here. There we go. So the first thing we're going to do is exclude any participants who have too much missing data. The rule's still 5%. Remember, in this we're calculating percent valid. This is for participant for each row. And I could probably tell pretty quickly that I don't actually have any missing data. There are only 40 participants. Minus, give or take any spaces, weird spaces in the data set, which is something fun that Excel has been doing with this like CSV Mac to Windows conversion. But we're going to use the formula we did before. So we're going to do count A, so count the number of valid things, divided by the number of things we're looking for, so 3 times 100 to get this in percent. Remember, from white to black, double click. I could tell kind of quickly that I've got everybody in the data set. So I could sort. Now if you do sort here, tell it yes, expand the selection, don't randomly sort the data. And I have 100% either way. So we're doing good. Let's calculate now by column. And if all of the participants have 100%, then the column should also have 100%. But we're going to just test this anyway. So equals count A, highlight all the data, close parentheses, Now I know I have 40 people, so divided by 40 times 100. And then I'm going to drag and drop across here. And you can drag it all the way over here, that's fine. So I don't have any missing data. So that makes life easy. Now I could take these. Now, since I don't really have any missing data, I don't really have to copy this into a new tab, but it doesn't really hurt you either. So let's look at outliers. Now, in the video, I talked about Mahalanobis again, which still would be really useful if we could do, but we can't because Excel will not calculate that sort of multivariate statistic. And then we talked about Cooks and leverage. Now, remember, Cooks is the combination of influence and sort of discrepancy at once. And leverage is like a lever on your car, trying to drag up your car. It looks at how much influence each person has on the slope. Unfortunately, there's not a good way to get those two values out of Excel either, but there's going to be kind of two things that we can do here in Excel and in JASP to kind of mimic those effects. Okay. And the first one is something you have been doing. So we're going to calculate Z-books, Z-attendance, and Z-grade. Just seeing if there are outliers within each one, and this is what you've been doing. So equals average. Oops, I'm sorry, I almost forgot the important part. So open parentheses, click on the first data point, minus, now we're going to use average of the whole first column, close both parentheses, divided by STDEV, open parentheses, whole first column. Okay. So z-scores that you've been doing, remember, change from white to black, drag across here. Okay. That gives me all three z-scores at once. Woo! And then I can go from my white arrow to my black arrow, double click, and get all the z-scores for every person for every predictor and y value. I'm going to highlight all three of these and do some coloring here so I can make it easier for me to see. That's under the Home button in Excel. Conditional formatting. Highlight cell rules. Greater than 3. Or we can do 2.99. Let's do that again. Conditional formatting. Highlight cell rules, this time less than negative 2.99. What I'm going to do is I'm going to kind of scroll through and I'm going to look at see if we have any. Okay. If you have thousands of data points, it might be easier to use filters because you can filter by color. Okay. And it turns out that I don't have any. Okay. This is where it can get tricky. In the lecture I talk about, it's sort of 2 strikes you're out. So if we have 3 criteria, Cooks, leverage, and Mahalanobis, we can say, well, if you're outlier on 2 of them, I'm going to kick you out of here. And since we don't have that, what can we do? Well, we can think about if they're an outlier on more than one variable. Or if let's say we have 3 variables here, if they're an outlier on most of the variables. So here we could also use 2 strikes you're out. Or you can kick them out for being outlier on any one variable. I probably don't recommend that. I would recommend kicking them out if they're an outlier on more than one thing. Because it's not just that their score is extreme on this one particular variable, it's that their scores are extreme on a lot of the variables. So you're really looking for a combination of z-scores that are bad. So no hard and fast rule here, and it should always tell you in the assignment what to do. But we could kick them out if they have multiple bad variables. Now, there is something that in JASP that'll let you kind of also calculate outliers. And it's a standardized residual. So we will come back to that once we get to JASP. We'll see if it matches what we just did. So I didn't have any missing data and I didn't have any outliers. Phew. Let's move on. Make this our final data set, which is still everybody. Let's calculate some more stuff. Right, so let's click Data, Data Analysis, and we're going to do Correlation. Right, I'm going to highlight my 3 columns. We want to say grouped by columns, right? So we get the correlation for variables. It labels in the first row. Remember, this is additivity. Okay. Additivity is especially important for regression because regression will actually blow up and not run if your additivity is poor. So first thing I'm going to do, I actually should not probably have included grade. So I'm just going to kind of mark it out. Now I'm marking out the DV. Why am I marking out the DV? Well, you actually want the IVs to be correlated with the DV. That is the whole point of regression. IVs correlated with the DV. So instead, I'm really just making sure that the IVs are not too correlated. So write that down. IVs not too correlated. It's the same rules that we've been using, 0.9. Because then, if they're correlated at 0.9, what that means is that they're related at 81% of the variance. That's just freaking ridiculous. Like, why are you wasting your time using both variables when they're so correlated, right? Pick one, run with it. Okay. Here, these two are related at 0.44, so that implies, that they overlap in like 20-something% of the variance. So hopefully those are different enough. Okay, and we'll see. So we don't have any problems with additivity. Now, I'm going to take a quick break, and normally here we would go through a whole bunch of schmeh on how to do residual graphs, standardized residuals, histograms, normality, QQ plots. And we're going to put a pause on that. And so you can still do all of those things that we did before in Excel, especially if you're like, I'm comfortable with it, I like it, I'm good. Or you could probably make your life just a touch easier and do this in JASP. Okay. So let's pull up JASP here. Because we still have to decide if it's normal, linear, and our two homogeneity, homoscedasticity problems. Let's open that data set. And since it's the same one, I can open data.1. Since I didn't really do anything to it. Now let's run the analysis. So I'm going to click regression, linear regression. Our dependent variable is grade. Both of our IVs go here in this covariates box at the same time. Okay, ignore all this for a second. Let me make this bigger. Okay. Ignore. Under here, under assumptions checks, check it out. Let's say I want to check out normality. It's the first one I've written down. So click residuals histogram. And I'm going to click standardized residuals so that the bottom is centered on for 0 and it runs here -2 to 2. So there's that histogram chart that we've been making in Excel using the histogram function. And now, look how nice it is plugged in for you. Now, damn it, why can't the ANOVA function have that? There's a lot of reasons other than they just haven't put it in there. But when we did ANOVAs, we created a fake regression. Remember, we did all this fake stuff. I kept saying it was fake, it's fake, it's fake. Because once you get to real regression, now it's a little easier. Because I have ones that are specifically IVs and specifically 1 DV. And so standardized residuals are how well we're predicting the DV. With ANOVA, we were concerned about our continuous variable. And we wanted to know that that continuous variable was normal. But we didn't really have anything to compare it against. So we made up a randomized data set. And that's why we did all this fake stuff. Was because we were making up a fake regression. So now what we can do is use the real regression, and thankfully it's programmed kind of nicely into JASP already. So I know it sucks. But like I said, if you're like, oh, I got the Excel thing, don't throw this new curveball at me. You can do everything you've been doing in Excel. You would just treat all of your IVs and DVs as continuous variables and just truck along. You will get a slightly different answer because here we're not using a random variable. But generally the answers are only slightly, just like a little different. Your pictures will look different. Right? And so sometimes interpretation can be a little different as well. I think this is easier, and I wish we had it for ANOVA as well. All right, anyway, there's our normality chart. Check, 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 it looks good. To get our linearity chart, we're going to click QQplot. Now, QQplot and PPplot, basically the same thing. And it draws the line on there for you. Look at how nice and normal and linear that is. Woohoo! And then we're going to click Residuals versus Predicted. And that popped up at the top. The residuals versus predicted values will give you the sort of standardized residual scatter plot. So for homogeneity, they conveniently also drew you a line here at 0. So we're going to look at this side, the standardized side. And remember, you want the spread to be roughly even around 0, and then roughly even around the middle. So you kind of gotta see, here's the middle, and it looks pretty good. So homogeneity is okay. Homoscedasticity is really super like big flags, homoscedasticity signs, arm waving galore right now, because we want to make sure that the spread down y, which is our predicted values, is equal all the way across y. Because if it starts small and then gets wide, or the other way around, or if it looks like a UFO, that implies that there's something going on that we're missing. So why is the spread inconsistent? There's lots of reasons why heteroscedasticity can happen, but we want to make sure that we don't have that problem. And then in this particular case, we're looking pretty good. I mean, there's kind of this weird like spot right here where there's nothing, but I would say overall this one's generally okay. And so we were able to check normal, linear, homogeneity, homoscedasticity, bam, bam, bam. It's the bottom 3 right here, okay, including the standardized one. And all that does is it puts this bottom in a number set that you're used to seeing. Woohoo! The other thing that you can do, oops, sorry, not options. I think it's under statistics here. It's under residual. You can click case-wise diagnostics. And that's actually going to give you any person whose score overall is a z-score of 3. And what it does is it combines all of their IVs together and sees if their prediction value is a z-score of 3, which means that you can't get that shit right at all. Like, you're not predicting them. Whereas what we did here, under no outliers, is we just saw within each variable how far away from the mean are they. Here what we're doing when we click on this case-wise diagnostics button is we're looking at how bad the prediction is. So we can combine that with our z-scores and say, well, this person's got, usually if they're an outlier on 2 of the variables, you're not going to be able to predict them. So they'll also pop over here. And what they mean by case number is what line they are on the data set. Okay, whoops, I don't want to do that. I could also calculate the correlations in here. That's just as easy as Excel. So let's see here. I'm about to have to do this twice. So I think if I click on it, maybe it'll come back up. There we go. Okay. So I've checked all of my assumptions here, and we're looking pretty good. So let's try actually looking at the analysis now. Okay. So what I've got is the model summary up here. We're going to come down over here and click R-square change, because remember that'll put our F statistic up here where we can use it rather than looking down here. We've got our coefficients, and we definitely want part and partial correlations. Let's copy all of that into Word here. Now, remember on a Mac, it's going to ask you if it's okay to access the files. So I hit select and grant. That's going to be cutting and pasting the pictures. You can also do screenshots. I don't think it asks you this on Windows machines, but if it does, say yes, because otherwise you're not going to get your pictures. And I don't even understand why these pictures come up at the size of Mars. But what I can do is click picture format. Just tell it to be like 4 inches or something, smaller. I think screenshots might be a little easier. I also love screenshots, but I can make these plots just a little smaller or leave them huge. That's fine. I don't care. Okay, let's look at this result though. So we're interested, first of all, if the overall model is significant. That's the first thing that we need to review. So I'm going to come up here to my linear regression box, and I'm going to write this up as an F statistic, because F statistics match ANOVA and regression. Remember, ANOVA is just a special type of regression. I'm going to do 2 and 37 equals, and I'm going to use F change here. So we're using this out here. Actually, the whole shebang. So it's 9.06. Our p-value is less than 0.001. And our r squared, excuse me, is 0.33. So this is a large effect size. So that means the overall model is significant. Books and attendance significantly predict grade and course. So that overall model is significant. By using these F change, I can ignore this ANOVA box, but now I'm going to be interested here in the coefficients. So if the overall model is significant, which one is better? Okay. So let's talk about attendance first. Okay. That B value is 1.28. What does that mean? So I'm getting that from here. Right. So remember, unstandardized is B, standardized over here is beta, and we're also going to use these two numbers here. So that means that for every one class that you attend, your grade increased 1.28 points. So remember, the interpretation of B is for every 1 unit X, for every attendance point, there's B units in Y. There's 1.28 grade points. I'm going to use T. What's my degrees of freedom? Remember, it's the second number from up here, so it's 37. Is 2.19 if I round up. P equals 0.04. Now what we're going to do is add PR squared. I'm going to come back to that in just a second. We're going to do everything up here with this box, but we're going to go there, so I'm going to leave it in there. Now for books, the B value is 4.04. So for every book I read, I got 4 grade points. That seems like a lot. So we'll use the standardized coefficients here in a second to determine if we think that that is like, which one should I prioritize my time, right? So it's 2.30, P equals 0.03. Okay, so they're both significant. So for attendance, every one class gave me 1.28 points. For books, every one book gave me 4 points. But books and attendance are not on the same scale. Attendance was like 0 to 20 and books was 0 to 4. And so clearly books is like taking more time. So how do I know which one's better? Well, I can come over here to standardized. So this is beta. And beta is a z-score unit. So it can be negative and it can be bigger than 1. So if you get a 2.85, it is not wrong. Okay. It's a z-score. It's not a correlation. And it shows me that books is a stronger predictor. Right? And p-values tend to match here. So it's a stronger predictor, but I don't know if I would say it's that much better because look at the difference. It's 3.3 and 3.5. I'm sorry, 0.33, 0.35. So, they're not that different. There are ways to test if they're significantly different from each other, but I think just kind of eyeballing it, I can tell here that they're really not that different. Even though with the B values, the unstandardized values, it looks pretty different. And so that's where beta is super handy. It's kind of going, well, they're about the same. Okay. Now they're both significant, so they both are significantly predicting grade, holding the other constant. So this is every book that you read ignoring attendance. And what I really want to do now is add, of course it goes across the page here. Let's see if I can make it smush up. Nope. Is add part and partial correlations. Okay. So this to me is the worst naming, and they carried the bad naming from SPSS over to JASP. So part means semi-partial, and partial means partial. So we're interested in partial because we want PR, not SR. And remember that partial is always bigger than semi-partial because the denominators are different. So we're always going to use the first column here. Okay. Now, this is PR all by itself. It is not PR squared. And we want all of our effect sizes to be in the same system. So we're going to take 0.34 and we're just going to square it. Oops, leave those decimals in there. So I got 0.12. You notice I don't have zeros in front of any of these because they can't get bigger than 1. So it's 12% of the variance not accounted for by anything else. And this one's 0.35. And that's also 12% of the variance not accounted for by anything else. So if you weren't convinced that the beta scores showed that they were approximately the same, the variance shows that they're pretty damn close too. Okay. So they are each 12% of the variance not accounted for by anything else. And I keep saying that because it's important. Because if I come up here and look at R squared, it's 0.33. Well, 0.12 plus 0.12 is 0.24. So what happened to the rest of it? Okay, so don't add up the PR squared values. It's very tempting to think if I partition up all the variance, it'll add up to R squared. And that is not the way this works. Your PR squared values can add up to more than R squared. They can add up to less than R squared. They can do whatever the hell they want. So remember that R squared is all of the X's predicting Y. So 33% of the variance in Y, in grades, is due to books and attendance. And these interpretations here is it's 12% of the variance is due to attendance, just ignoring everything else. Okay. Books, 12% of the variance is ignoring everything else because the numerator and denominators are totally different from these two statistics. But what they do, the purpose of each of them, to me, R squared gives me an overall picture of the entire equation, the overall model. PR squared allows me to look at like individually how useful is this controlling for everything else. So I know that they're both 12% of the variance, so they're about the same. All right, so you can look at this right up because that's all that we've got going on here for these. And I will change the outlier piece just a bit. Magic random F here. But you'll notice that I talk about the overall model is significant. So I've got all these values that we just talked about. And then I write up each of these, and the numbers change here just a little bit because I think I'm a little bit of fancy math, but it's 12 on both of them. Okay. But you'll notice that in here I have beta, okay, instead of B. Doesn't matter. You can use B or beta. Just be consistent. So either way, be consistent. Okay. Your cheesiness over for the day. And now what kind of picture can I create of this data? Well, there's really not a good one. And even the one that I present on how to do this in R is still not very good. And I don't know that too many people make these sorts of charts, because you'll see that like it's not even an option in any of this stuff. But I'm going to kind of show you how to make a chart. Like if you want to create a picture of what does this data kind of look like, what you can do is take the predicted scores and compare those to the actual Y scores. Okay. And then it's a little bit of a pain. So we're going to do this in Excel, but we're actually going to do this in Excel in the data screening sheet that we've been working on. Okay. And we're creating a graph of predicted scores versus actual Y. Okay. And we're using those predicted scores as like a sort of a substitute for each of the X scores, because I can't do X on the X-axis because I have more than one X. So I could make a correlation picture, a scatter plot of books and grade, attendance and grade, but that doesn't give them both to me together at once. Okay. All right, now to do that, what you want to do is something you've actually been doing as part of data screening. So we're going to click Data, Data Analysis. I'm just going to hit Regression. And we're just going to use this as a highway to graphs, if you will. So click Regression. I want to use Y, so I'm going to try it here. Maybe Excel likes me a little better. So Y is your one Y column. Click here for X. Highlight both of our X variables. Now this doesn't always work for me because of the labels issue, but we'll see if it'll do something good. We're not going to click any of the plots because I don't need them because we made those in JASP. We're going to click OK and hope for the best. Yeah. It doesn't like me. And I know we've been having Excel issues all semester, so I guess I feel a little better knowing that I'm not the only one it doesn't like sometimes. Apparently I said something close enough to hey iPhone thing. Right, let's hit that now. Okay. So I have zero idea. Oh, and I didn't include the data I needed. Why that seemed to work and nothing else seemed to work. So I lied to you. I'm sorry. There's one more thing that you need to do. Yeah. So back to that data analysis. It's the same regression I had open, but make it give you the residuals, because otherwise we're not going to get some of the numbers we need. Okay. Now, it gives me my predicted score, and then it gives me my residuals. I don't really care about the residuals. So what we're going to do is we're going to kind of make a new sheet here and just call it graph. It's very exciting. And we're going to take the predicted scores. So I'm going to highlight all of these. So if you hold down Shift, Control, or Command if you're on a Mac, and down, you can highlight everything at once. And it gave me 39 observations. I should have had 40, so I think I screwed that up. Derp. I think I must have left in, yes. Good grief. Okay, let me try this one more time. Third time's a charm. Even I make mistakes. I'm gonna hit Data Analysis, Regression. I did it without the labels, so I'm gonna turn off labels this time. Okay. Input value must complete. Oh, good grief. Where were we at? Cancel. You guys, having all the problems. Let's try this again. So data analysis, regression. I'm going to highlight all the scores. Okay, that looks pretty good. Here I'm going to highlight all of my A and B. No labels this time. And give me the residuals. That is the final say here. Click OK. There we go. Now I'm going to highlight my predicted Y. This time 40 cells. Thank goodness. I'm going to stick that just up here in B. I meant to highlight the word predicted. Okay, so there's my predicted score. I'm going to come back over here to my final one and actually pull Y. So this is actual Y. So it's great. So we have our, and I actually want to put that there. You'll see why in a second. So we have our predicted score, which we're going to put on our x-axis, and our actual score, which we're going to put on our y-axis. So this is the combination of grades and attendance. So given your grades and attendance, this is what it predicted that you would get. You actually got a 56, so we're not still doing so hot right here. But 61 to 64 are doing pretty good. So now let's make a scatter plot. So I'm going to highlight both of those. Insert. Over here, scatter plot. Boink. give us a scatter plot, and then we would clean this bad boy up. So I'm going to delete that. I'm going to get rid of all these stupid lines. Right. We're going to add X and Y axis titles because we love to give things titles. Those are easy points. Right. So you can call this predicted, or essentially books plus attendance. Kind of depends on how many predictors you have. So sometimes just word-wise it won't fit. We're going to call this actual grade here. And I probably want to cut off, so I'm going to double click on this axis. I'm going to cut off that minimum value here and make it 40 because we just don't have anybody in that lower range. Okay. And we'll do the same thing here. Okay. So we're just going to cut off those two areas where we don't have any data points. So we're only going to show you the data points that we know we're predicting. I'll right click and add a trend line. And that trend line shows you my two X's together. So that's not really a trend line of like grades predicting, books predicting grades. That's a trend line of like both of those things together predicting grades. You can actually tell it to display the equation, but it's going to be incorrect because it's only got one variable instead of the multiple variables that we're doing. But I like this chart. It's pretty nice. So the only other thing I'd want to tell you to do is to make it not be in the stupidest font in existence. So let's make it a little bigger here. And we could cut and paste that into Word given some, word difficulties. I actually figured out here that the border around it is actually coming from Excel. So I can turn it off on the Excel end by clicking on Format and telling it to not give me a stupid border, which is fantastic because then when I copy this bad boy, go over here to Word and say, see figure 1. So I have see figure 1 for representation of the data. Bum, ba, bum. No stupid border. So you can get rid of it in either place. The only other thing I think we talked about was making the lines here a little darker. But that's because in bar graphs it doesn't include the line, so you can also change that. I'm okay with them being a light color. They just need to be there. And when we were working with making bar graphs, they just didn't exist. So that is a great graph. Then what we can see is that we're not really predicting anybody to get much above a B, right? So there's nobody over here. But people are clearly getting A's. So we're not really predicting this group of people very well, but we are predicting these people down here really well. So the nice thing about these graphs, making them in the style, is that I can look at what types of people on Y I am predicting well and not well. Okay. I don't know that people always print this sort of thing. I find it helpful just for my own vision, so we're going to make these for our write-ups. All right, so we've covered everything start to finish. Now power, we did data screening, and a new and improved and faster and yay happy is data screening. Talked about how you're going to look at the model, overall model, and then the individual predictors for post hoc analysis, a little bit on the write-up, and then how to make a graph for this analysis.